Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at the new Tektronix AFG31000 series arbitrary waveform generator. This is a two-channel instrument, a really interesting instrument with some unique built-in functions that allows you to monitor the waveform that you apply to your device under test live on the screen itself. Aside from that, it has some advanced ARB building capabilities built into it. What Tektronix wants you to do is to decouple you from the traditional PC where you have to create your waveforms and then download it into the unit. They want you to be able to do all of it directly in the unit itself. That's a pretty big goal and a lot of limitations you have to overcome to make something like that happen. But it's a really nice instrument. We're going to do a full teardown of it. We're going to do some extensive experiments with it and see its strengths and weaknesses so you see how it fits in your application. So let's get started. And here is the Tektronix AFG31000 series arbitrary function generator. This particular one is model AFG3152, which is the highest model, 250 megahertz bandwidth, 2 kilosamples per second per channel. As you can see, the look and the feel of this instrument matches the latest design that Tech has been putting on the market, obviously under the same industrial design portfolio. And it looks like the MSO5 series and 6 series oscilloscopes, for example. It has a very large capacitive touchscreen in the front, the largest in its class, and this allows you to interact with the waveform directly on the screen. Tech has essentially been marketing this as being untethered from the PC, meaning that you can build your waveforms and manipulate them and assemble complex waveforms directly here on the LCD screen without having it connected to a PC. So we can take a look and see how well that works. Other than that, I think the screen is very nice. We have power button USB, of course, and channel 1, channel 2 outputs right next to each other, and trigger input and output. I think these are the good choices to have on the front panel because these are the ones that you most likely are going to be dealing with often, and this also allows you to synchronize several instruments together. The front panel has a combination of advanced and basic functions. A lot of the waveforms and buttons are illuminated, which is really helpful when you want to just at a glance figure out what is being done. All the basic functions are here, and then advanced functions are primarily controlled through the GUI, as there's a lot of contextual things that come up as you're building the waveforms. The InstaView button at the top, which we will take a look at as well, rotation knobs and buttons and going to home and back, and a keypad, which is very nice and useful, even though a lot of times you can just enter it on the screen. It's nice to have there on the side. It's definitely a very nice looking instrument, and the on and off buttons for the channels and swapping the channel settings are also available, which is pretty handy. A lot of times, again, you want to see what is being output or if the output is enabled or disabled without having to go through the menu, and you can see it from far away, especially if you have this tucked away somewhere in the lap. And here's the back of the unit. As you can see, nothing unusual going on. We have the AC line input, of course, GPIB, USB and Ethernet are all standard as far as I know, and we have the external reference input and output, so obviously you can cascade things and give it a 10 megahertz reference so that it's perfectly aligned to another instrument. This is important, especially when you are syncing multiple of these. And then there is an external modulation input both for channel 1 and channel 2, which we're going to take a look at. There's also an add input, which adds a signal to channel 1. This allows you to superimpose something directly on the waveform being produced on channel 1. This is really handy, and I'll show you some experiments with it as well. Other than that, I think everything looks very nice. So let's go ahead and take a look and see what's inside of it. I'm going to take it apart completely and look at the boards and analyze it. We're going to do that before any of the experiments, and let's see what it looks like on the inside. Let's go ahead and take a look at what's inside the unit. I've taken it completely apart and I've taken the main board, and I'm going to show you the construction in just a second. Typically, I do the teardown after I've done complete experiments on the unit, but this time we're doing that first, and I thought it would be interesting to see if we can extract some of the behavior of the device before we test it directly from its teardown. Now, this is the main board, and as with any mixed signal board, it's going to have a lot of different components placed in different places, but this is all strategically done in order to maintain good RF performance. So at the very left side, we have a lot of DC-DC converters to produce all the different voltages required for the board to operate, and on the right side we have some more voltage regulation and DC conditioning circuits. As you can see, they're kept as far away from everything else on the board as possible because these are the noisy blocks, and these are the blocks you don't want to interfere with the RF and the analog output. The next components are going to be memory and some digital circuitry. Now, this digital circuitry is obviously going to also be potentially putting some noise on the analog devices, but at the same time, these are all using differential LVDS signaling. So in their impacted footprint, EM footprint on the board is actually not that bad because everything is differential. So this memory is going to hold all of the arbitrary waveform and the data that you want to transmit directly on the RF channels. And it's obviously, once you put everything in here is going to be grabbed from the memory through the FPGA and put onto the DAC at full rate. So you're not going to do anything else once everything is stored in the memory. The FPGAs themselves may potentially manipulate the data depending on what's being displayed before it's applied to the DAC. Now the interface between the FPGA and the DACs is a JSD differential LVDS type interface. These two DACs are completely independent analog devices, AD9739 TX DACs, and these are 14-bit 12.5 gigasample per second RF digital to analog converters. The reason they are called RF digital to analog converters is because everything in the back end can be essentially digital up until the output, and you can directly connect the output of these TX DACs to antennas if you wanted and produce a radio and do transmit and do modulation and do data. And the reason this is very convenient is because if you're building let's say some kind of a communication device in the ISM band, then you would only need one SoC to do everything. You don't need to do mixers and so on. Everything is done in the digital domain. But it's not how they are used here. They're used in their baseband mode, which can produce signals from DC all the way to 1.25 gigahertz. Again, they're not used all the way to those frequencies. They back off the output frequency in order to be able to maintain a 250 megahertz bandwidth. As you can see, we have two completely independent channels, and the output of these DACs are then taken into a series of mechanical relays and switches and attenuators in order to meet the different output amplitudes and working operation of the circuit. This is very common. You've seen me discuss this when I've taken apart different kinds of arbitrary function generators. This is a good way to achieve very high linearity and dynamic range by using these mechanical relays. You can see that these are essentially symmetric, even though they're not laid out symmetrically, and this is due to space constraints mostly. But you can see the signal path, no pun intended. For both of them, they have the same number of relays on both sides. We have two output amplifiers, and even though the heat sinks are on this side of the board, the devices are actually on the other side of the board, and I'll show you that. This technique of using heat plugs through the PCB to take the heat to the other side and have all of your heat sinks on the same side of the board is a common technique in order to do some thermal profile management. And of course, note that the heatsink fins are all directed in the same orientation because the airflow will have to go through all of them. And even these ones, even though from your angle I don't think you can see, the fins are indeed pointing in the same direction, and these devices are most likely voltage regulators and so on. So if you look over here, there's a section in the middle which is common to both channels, and this is going to perform some analog functions. This is a 18-bit DAC as a high precision audio DAC, most likely used to generate some precision DC offsets signals to be applied, or maybe even some low frequency signals applied, but it is obvious that it's common to both channels. After that, we have an analog mux. This is an 8-channel analog mux and some op amps. So whenever you see a single output DAC and an analog mux and some op amps and so on, you potentially have some kind of a sample and hold circuitry where you store the value and then mux it through 8 different channels. That's potentially one way that it is being used, and this can be used to apply offsets and trimming and so on, and potentially get good THD performance from the output drivers through this common section. There is also an 8-channel 24-bit delta sigma ADC here, which is used to sample potential thermal information and offset information and biasing information fed back to the main controller. So you can get an idea of what's going on, and potentially these guys are all working together in order to be in some kind of a feedback to get the highest performance from the outputs and apply the DCs required. So that common section you can see is used on both of these, and then I'll show you the other side of the board so we can see how the outputs are taken. By the way, the outputs are here and here, so you can see the trace going into these two sections in a fairly symmetric way. Now here's when things become even more interesting, because we have two chips here, one over here and one over here, fairly close to the output of the device themselves. Now these are tech labeled, meaning that it just says tech and a certain number afterwards that I cannot find in the data sheet. These are most likely made by tech, their own ASIC potentially. The reason I think it might be their own ASIC is because, remember, this instrument gives us InstaView, which is a direct representation of the output signal being applied to the ports so that you can see if you have any mismatches in the impedance, so you can monitor your own waveform. That means that you need to somehow get the signal from the output, sample it, digitize it, and display it. So you kind of have a mini oscilloscope, 2-channel oscilloscope built into this instrument at the same time as an arbitrary waveform generator. So I think that these might be the front end of those sampling devices in order for you to be able to look at that signal and condition it so that it can be digitized. Every oscilloscope has, of course, a front-end analog section, and this may be that front end for this instrument. Now, it may not be, but I think given that there are two of them fairly close to the output, it is possible that at least it is in some way involved in the InstaView circuit. These are not analog to digital converters. Those are on the other side of the board. They're most likely just analog conditioning devices. Now, everything else over here is pretty straightforward. There's a couple of other interesting things. There are two connectors here which pass data back and forth to the main other digital board on the other side, but they're not quite the same. This one is close to the BNC connectors at the back of the unit, which have the modulation input-output go directly to the back of the unit, which means that these still process some analog type, mixed signal type device signals. And you can see here we have some isolators, and this guy over here is an ECL programmable delay chip used to align clocks and data coming from somewhere else. And this is not surprising. Whenever you have connectors and something and you need to align multiple signals, it might be very difficult to maintain an alignment over calibration coefficients, over process variation. It might be used to do that alignment, or it might be used to do some alignment in order to get the trigger and the markers and so on aligned between different channels. So that's another possibility use of this unit. Other than that, I don't think there is anything else that I was looking at. And some power connectors. Oh, and this is interesting. These are this is where the screws go that connect this to the chassis. And this is a grounded pad essentially because it's connected to the screw. But you don't necessarily want to treat it in a normal ground. Look at all these capacitors that are here. This is an entire capacitive network that couples this screw to the rest of the ground. And this is very carefully designed to get a precise frequency response of the ground. These things take a ton of simulation and care in order to ensure that they meet a particular coupling structure and particular frequency response. It's very interesting. I'd love to figure out exactly what problems they were having to do this. I mean, we do this, of course, ourselves whenever we do designs. And here's the back of the board, and we can finally see the rest of the components that I was referring to. So here are our analog outputs, channel 1 and channel 2, and trigger input and trigger output. Next to the trigger output, we have a driver IC, which is to be expected. You want to have something that boosts and ensures proper impedance of the output trigger, so you can get nice edges on that. And then on here, you can see two ADCs. These are the ADCs I was referring to. These are 8-bit 500 megasample per second analog devices, AD9484. And there's two of them because we have two channels. And I believe this is what finally closes the loop on the InstaView circuitry in combination with potentially those TIC chips I was talking about earlier. What is a little bit surprising is how far these are from the output. But again, you have only two ways. You can either put the ADC really close to the output and have the digital lines go all over the place, or you can route the analog to the ADC and then have it close to the FPGAs and the SoC processor there, which is kind of makes more sense, and that's what they've done it here. And that's why I think that the conditioning IC is sitting very close to the output, and then the signals, once they're conditioned, boosted, and amplified, they're sent back to the ADCs here, and that's how you close the InstaView loop. Remember that you cannot sample the output of the DAC. That's kind of useless. You have to sample the output right at the connector there, because that's where the impedance is going to make a difference. That's why it needs to go all the way back there. So now the output driver section is also fairly interesting. It's worth discussing. These are Texas Instrument devices. These are THS3491. These are 900 megahertz, 500 milliamp high power current feedback amplifiers, which can be used in various configurations. And the most popular one is to use 3 of them in order to create very linear, very high output signal swing and very high bandwidth amplifier sections. And you can see 1, 2, 3, except that the third one is not populated. It is possible to use this in a dual configuration as well, which is, I think, what is being done here. These guys have temperature monitors and have excellent linearity and some sensing capability, which I think is what is being used by the analog and digital converters on the other side of the board in common to both channels. And you can see there's 2 of these. And I think that's how everything eventually connects to each other. I'm going to show you the block diagram of this. I'm going to put it on the screen as we're talking about this. Right over here is one of our connectors. You can see drivers responsible for that to do the communication with the back of the FPGAs. You can see the rest of the traces for the JSD interface. There's supposed to be 28 of them, I believe. 14 are on one side and 14 are on this side, carrying everything. And I think that's about it. It's a very nice board. Clearly, a lot of thought has been put into it. You're basically making an oscilloscope and an arbitrary waveform generator simultaneously in one unit, even though the oscilloscope doesn't need to be ultra high performance, just enough to give you a waveform representation. And here is the main digital board. This is where the application and the firmware and the LCD control and everything is going to be. This is what's also the interface to the user. So if you look carefully here, you can see this chip. This is an NXP dual Cortex A9 ARM processor with a lot of other peripherals built into it for essentially multimedia processor, industrial applications included. and this is running at about 800 megahertz. So there's going to have some memory, flash memory, some RAM, of course. Now every data that you put in and out of this instrument essentially has to go through here before it is passed to the FPGAs and ultimately producing an analog output. So of course all of this interface is going to go through here, and that's how this board talks to the FPGA board and exchanges information. This chip over here is a National Instruments GPIB controller, lattice CPLD. These are all tied together for some logic and so on. They're connecting ultimately to the main processor. Here is our real-time clock battery there. Here's the AC input. Interesting to see that it is on this chassis. Some protection, fuse, and interface to the main power supply, which is shielded. I'll show you that in just a second. Main power switch, nice, completely separates the AC line from the rest of the circuit. USB over here. On the other side of this, we're going to have the Ethernet controller IC. Again, room for a shield, which is not populated. And if you look carefully here, these analog BNC connectors, which are the modulation ports and so on, they are all on a totally separate plane. If you look carefully through the PCB layout, you can see that this is all isolated, and that's because this goes directly through here to the analog board. This is still essentially part of that analog board, and that's why if you look carefully here, you can see a similar grounding, handling the ground connection just in a similar way, because this is still part of this part of the board. Whereas with these guys, you don't need anything like that, because this ground is nowhere near as critical. It's the interface between this ground, you can see another one over here, with respect to the rest of the system. Very nice, and tons of work must have been going into designing that. Other than that, really nothing unusual. Everything's pretty straightforward. So we're going to continue putting this back together so we can see the rest of the chassis. Here is some more good example of a floating RF ground that's coupled to the chassis capacitively. You can see this is the front panel. These BNCs are DC floats compared to the rest of the chassis, but of course coupled very carefully to the main chassis ground via the stitching of this capacitor. So this is all over the place in this design. And here's the power supply module before we put everything back together. So here's the everything else I already assembled, and the power supply is most likely not made by Tech. I'm not going to take it apart anymore. It's just a regular switching power supply. Nice attention to details, ensuring that these cables do not eventually get scored by the sharp metal. Big RF absorber section here, which is quite interesting. This section sits right on top of the analog section, so they have added some RF absorbers to not allow anything propagating through this, and basically any energy being exchanged between the two boards, which is quite nice to see. And a fan over here, nothing unusual about it. Let's put it back together and finally do some tests with it. Alright, let's go ahead and turn it on and see how long it takes for it to be ready. It has, of course, a hard power button, as I explained, and it's going to go through a quick boot up sequence. As you can see, big nice LCD screen, and it's important sometimes how fast instruments come online and ready to use. You know, if you're turning them on and off regularly, most of the time these things are often actually kept on all the time. So there you go, it's going through some self-test, I believe. You can see all the buttons light up, and there it is. There's a list of all the things it self-tests, and basically it's ready to go at this point. So now it's going to go to the basic menu. From then you can choose whether you want to go into advanced mode or basic mode, and you can also go into the app builder directly. So under basic mode, it's going to be a very simple arbitrary function generator, and even though it's a simple interface, it gives you full control over what's coming out of the waveform. So we can start with the basic mode and do a couple of quick experiments with it, and then jump into some advanced waveform building. So let's take a quick look at the GUI in basic mode and see how it operates. Tech has obviously spent a lot of time trying to make the GUI very intuitive and have a nice connection between the buttons and the GUI directly, so that it is easy to use essentially. So we have channel 1 and channel 2, which corresponds to two outputs, of course, and you can select them by just tapping on them, and the border then changes color, showing you which of them is active. I think the border should be a little bit thicker so you can really see which channels you have selected. I've also noticed that this instrument can really benefit from a mouse, and there's a lot of little areas where you want to do manipulation, especially when it comes to waveforms, where a mouse would be quite useful, but I don't believe it is supported at the moment. So you can make one channel larger. Again, this is a touchscreen, so it's very intuitive, and this way you can see nicely the waveform at the bottom and more of the settings at the same time. You can also make the waveform larger, and this can be really handy once we enable InstaView, because this waveform is going to be updated depending on what's arriving at the device under test, and this unique feature can really benefit from having a larger display. As we can see, it can be easily done. Same thing can be done on the other channel there. So you can select the different type of waveforms directly from the buttons. You can see you can go through a ramp, or you can just simply select them from a drop-down menu. I wish you had a few more selections. It is fairly, you know, still has quite a few, but I think there are some competitors that offer even more waveforms directly built into the memory. You can obviously upload your own, but if you want to be completely untethered from a PC, the more the better. You can also do your waveform modulation, sweep or burst directly here as well, and all the settings get updated depending on which one you choose, and we'll take a look at that in detail. At the bottom here you have an additional menu which allows you to do things like aligning the phase, locking the channel settings together, copying the settings of a channel from one to the other. You can control the behavior of the channels. You can see exactly what the load is and what is enabled and what is not enabled. You can create differential signals very easily. You can sync multiple channels. You can go into the ARP builder directly into this. We will definitely do some of these experiments as we do more and more tests with it. So one of the capabilities of this unit, among many others, is that it can do FM modulation with a really wide FM depth. So let's go ahead and try this out. So here I have put the instrument in default setup. Let's go ahead and change the frequency to 100 megahertz so we can have a fairly wide FM modulation centered at a 100 megahertz carrier. I'm going to change this from continuous to modulation, which is pretty straightforward. Let's go ahead and enlarge it so we can see all the other settings. I'm going to change the modulation type to FM. You can also do PM and FSK, of course. And here we can choose whether the FM source is internal or external. If you use external, you have to drive the back of the unit. And you can, in fact, do that with the second output if you really wanted to create really unusual FM modulation profiles. Now, internally, it can go as high as 1 megahertz. So the highest value I can enter here is 1 megahertz. I cannot go above that. But with an external one, I could not get quite the way to a 1 megahertz. It seems like it's limited to about a couple of 100 kilohertz or so. Now the deviation here I can set to really large numbers. Let's go ahead and set it at 50 megahertz. Now you must appreciate that this is a fairly difficult thing to do. So we are basically modulating the carrier 50 megahertz deviation at a 1 megahertz rate all internally. Now, yes, of course, it may be able to say that it's doing that, but what is important is what is the linearity of this modulation? How well is it performing? And can we use it for radar, for instance? The reason the linearity is important is because if you cannot do FMCW with a waveform that is very predictable and linear, especially if you want to build a ramp, you cannot get very good response, because any non-linearity in the FM modulation translates to uncertainty in the radar range itself. So right now the output is disabled, and you can see a little bit of a residue of the FM modulation already present in the spectrum. So when the output is disabled, the DACs are obviously running, and whatever isolation you can get from the output amplifiers being completely turned off is what you're seeing here, which is quite good, and we're looking at less than 75 dBm, so it's not really a problem. Let's go ahead and turn this on now, and here it is. There is our FM modulation, and you can see it's exactly the width that you would expect it. It's supposed to have a 50 megahertz deviation, and it looks quite nice. But the key is now, what is the linearity of it? We can do demodulation and take a look at that. Let's go and change that. We can go to analog demod directly, and we can take a look at it here. There it is. I've already set it up, so we don't spend more time on that. Here's our signal over here, and here's the demodulated waveform. And look at that. This is a very nice sinusoid. And if you look at the deviation, is indeed reaching 50 megahertz plus and minus, so which is exactly what you would expect. And yeah, it looks good. But what is the THD? Well, we can go back over here and take a look here and check it out. THD is 0.1%, which is really, really good for such a broad modulation. Now, I can't even go higher than this because this instrument will not be able to really capture it. I can try a little bit higher. We can see it here on the spectrum. So I'm going to change that, let's say, from 50 megahertz. Let's try 75 megahertz. There it is. You can see it's now too wide because this can only do a real-time capture of 160 megahertz. So I believe that we're going to run into some problems. Yeah, it might be cutting the corners off, but nonetheless, we're still at 0.2% THD, which is again very, very good. As such a broad FM modulation is perfect for radar applications and where you need to be able to characterize something and see its FM response, of course. So now that we see this, let's go ahead and try a couple of things that are a little bit more complicated. So let's look at the brand new feature of InstaView on this instrument. So the idea here is that we want to find out what the signal is at the input of the device under test when it's connected to this function generator. And you can't always know this right away because this waveform that you see here is under the assumption that the load impedance and the source impedance and the cable are all matched to 50 ohms perfectly, which is of course not always the case. The source impedance of this unit is always 50 ohms, and it assumes that you're going to be using a 50 ohm cable. When those two conditions are set, they have created a clever measurement technique built into the unit to be able to tell you what the voltage is at the DUT. So the impedance at the DUT can be real or imaginary. It can even be nonlinear, and therefore you have no idea what is the signal arriving at the DUT. You cannot just simply rely on the waveform that you see over here. So what they've done is that at the input there is a unidirectional resistive divider. It's basically a coupler made of 350 ohm resistors. And that coupler over there allows you to measure at 3 different points the signal present here. And that's some of the circuitry associated with that I discussed and showed you during the teardown. By using some very simple math, you can figure out what is the signal at the DUT, because you know a few parameters. You know the impedance of the source itself, you know the impedance of the coupler built in, which is all 50 ohms. You assume that this cable is 50 ohm. The only information you're missing is the delay through the cable, because if the delay through the cable is comparable to the wavelength of the signal you're generating, then of course the signal at the end of the cable will not be the same as the signal at the beginning of the cable. So you need to know that piece of information, and luckily the instrument also measures that for you first and stores it, and then therefore can compute exactly what the signal is at the DUT. This is very clever, very useful, and it's patented for this particular instrument. So I have a little block diagram that I think I am going to put up so you can see where those 3 points of measurements are being made. So let's go ahead and through that process, and we can figure out how well it works. So let's see, what's the first thing to do? Well, first thing to do is press the InstaView button, and here we have it, of course, enabled on both channels. You can do it on both channels. Right now we're only going to measure on channel 1, and it can tell us what is the delay of the cable. Well, we don't know. You can enter it yourself if you want, but the easiest way is to just run it and test it. And it tells you that I must connect the output of channel 1 to the trigger input, and this makes sense because now I can generate a signal from the channel 1 and measure the trigger point on the input, and the time difference between those 2 events is going to be the delay of the cable. Let's go ahead and measure that. You can see it switches it to pulse, and that makes sense because a pulse is a good way to measure the delay. There it is. So the delay through this cable is 3.63 nanoseconds. Perfect. Now that I know this, I can enable channel 1 InstaView and press OK. Now you may not hear it, but it does a series of clicks, and the reason is because it's measuring 2 different points in the coupler that I mentioned, and in order to switch between those 2 measurement points, it does not use a solid state relay, it uses a mechanical relay. That's a little bit concerning. I can understand why a mechanical relay is used, because you don't have to worry about this linearity and all the problem that comes with having a solid state device. But at the same time, every time the signal changes, it's going to click back and forth a few times, make those measurements, and that can age that relay over time. So as long as it's not running continuously with a constantly changing impedance, it shouldn't be an issue. Just keep that in mind that it will be clicking left and right every time the impedance here changes. So right now it's settled, and I'm going to disable the output here, and you can see it does it again. Now you can see this is measuring live what is coming out. But let me connect it up to a test setup that I've built that has a very problematic impedance at the DUT, and see if this guy can actually measure that and give us the correct waveform. So here is our device under test. We have the input coming from the function generator into this T-junction. This T-junction is just a direct short. So at low frequencies and even up to a couple of 100 megahertz, you're basically having a direct short here. At the end of this, I have a capacitor and a diode, a germanium diode. Now the combination of the capacitor and the diode creates a nonlinear impedance. So not only do we have a capacitive component whose impedance changes with frequency, we also have a diode whose impedance changes with signal amplitude. So we have a very problematic input here, because depending on the signal amplitude and frequency, the shape of the waveform at the point here, this point will change, because it's directly loading the output of the function generator, which is 50 ohms. After that, we go into a 50 ohm power splitter, and the reason I'm using this is because it allows me to connect one side to the oscilloscope, and this directly goes into the MSO5 series oscilloscope, and the other side we have an attenuator followed by just a regular amplifier from mini circuits. The output of the amplifier I'm also looking at on the oscilloscope. The reason I'm putting all this over here is because the impedance looking into here at very, very low frequencies is going to be 50 ohms, which is going to match perfectly to the impedance of the source itself. And as frequency increases, the impedance looking in this direction is always going to be maintained 50 ohms no matter what. And that allows us to purely focus on the nonlinear and also frequency dependent behavior of the impedance here that's loading our function generator. So let's go ahead and look at all of this together. So let me just zoom in here so you can see what I'm talking about. Here's our function generator, of course. I'm using a Keithley power supply here to power this amplifier, and of course we're using the MSO5 series over there for the input. So let's go ahead and take a look at the signals. Okay, let's give this guy a try here. So right now the signal is at 1 megahertz and at half a volt peak to peak. Now both of these are below the threshold for which that impedance begins to matter. The signal amplitude is too small, the diode cannot turn on, so we don't have any nonlinear effect, and the frequency is low, and the capacitance doesn't really do anything. So therefore, we would expect the signal displayed here to match very closely to what is supposed to be actually applied, even if we didn't have any measurement capability directly on the DUT. Let's go ahead and enable that, and let's see what we get here. Okay, it did this measurement. I'm going to maximize this. So one complaint I have here is that there is no way to basically resize this. There's no way to fit it to scale. It just picks whatever scale and sticks to it. So it's very hard to see when the signal is small. But I think we're kind of stuck with it like this. But you can see that this is still very sinusoidal. But more importantly, the maximum value, which is 0.288, and the minimum value, which is 0.26, are roughly where they're supposed to be, because the amplitude is 0.548 volt peak to peak, which is what I set it to, which means that the signal at the DUT matches very closely the signal that's supposed to be applied to the DUT. So if I go over here and actually disable InstaView completely on this channel, you can see that that's basically the waveform that I'm supposed to get. You can see maximum 250, minimum minus 250, and the peak to peak is 500. So that's kind of correct. So we can go back and re-enable once again. There we go. So it does the measurement again. You can see we're getting exactly the same value. So that makes sense. But what happens now if I increase the amplitude from 500 millivolt peak to peak to 5 volt peak to peak, 10 times larger? Now what would happen is that the diode is going to kick in. So the nonlinearity of the diode is going to directly clamp the voltage at the DUT. And if you don't have InstaView, you wouldn't see that unless you have an oscilloscope connected. And we're going to compare that with the oscilloscope value. Let's go ahead and try that. So I'm going to enter 5 volt peak to peak here. There you go. It's going to measure again. But now, if I go ahead and maximize this, and you can check it out, maximize some more, and it doesn't always stay up there. Come on, you can do it. Yeah, this is a little bit annoying. They have to work on this so that this doesn't keep doing that. Oh well, anyway, we're stuck with this. So if you look over here, you can see now the minimum is minus 2.462, which is exactly what it should be. Remember, this is a 5 volt peak to peak signal, so the minimum should be minus 2.5, and it is, but the maximum is 0.68 because it's been clamped by the forward bias voltage of the diode. This is a nonlinear effect, and we're catching that at the DUT, not at the port of the instrument, but at the DUT. Right now at 1 megahertz, the phase of the cable doesn't matter, so the signal coming out of the instrument and the DUT are roughly the same. But there it is, as you can see, indeed we're catching this nonlinear effect. Now we can take it a step further, and we can go ahead and increase the frequency from 1 megahertz to 50 megahertz. And at 50 megahertz, things change because now you no longer have the impedance of the capacitor is going to become important. So if I go over here, you can see right away, again, unfortunately I can't zoom in anymore, but now the minimum value, 0.874 volt, is much closer to the maximum because the impedance is so small that the voltage is being completely filtered out. The characteristic of the impedance is completely filtering out the signal. So therefore now we have a much smaller amplitude at the DUT. Now what's really interesting is that if the cable was very long enough for it to appear as a short or open at the frequency of interest, you would still get the correct value at the DUT, because the phase is taken into account. Here, the cable is too short, but the phase of the cable also plays into how this is actually computed. So let's look at these signals directly on the oscilloscope. Here on channel 2, I have the input of the DUT, and on channel 1, I have the output of the DUT. By the way, I've done a full review and teardown of the MSO5. Definitely check it out. It's a really interesting instrument, and it's kind of become my default oscilloscope here in the lab. So let's take a look and see what happens to the signal. So here it is when it is half a volt peak to peak. And if you look over here, the minimum and the maximum values match. And remember, you should multiply those numbers by a factor of 2 because there is a 50 ohm power splitter directly before the oscilloscope. But anyway, so you can see the amplitude is 230 millivolt. It should be about 250, which makes sense. But this is when the signal is small, and this is exactly what the InstaView also showed us, that when you apply half a volt, the signal looks perfect. Okay, let's go ahead and increase it by a factor of 5 like we did on the DUT originally. There it is. I'm going to change this because it's clipping the scope, and let's go ahead and do this again and check it out. Look at that. That's exactly what the function generator told us, that it is going to get clamped at the very top, but the bottom swing of the signal is going to be correct. And if you look over here, look at that. At the top, you have 290, 200, and about 300 millivolt. Multiply that by 2, you get about 600. And then the amplitude is 1.45. Multiply it by 2, you get about 3. These numbers match what the InstaView told us, and this is exactly what you would expect. This is the output of the amplifier. It's got some interesting kink over here. I'm going to let you to figure out why that happens. I'll give you a hint. This amplifier has a bandpass response, not a low-pass response. Okay, so let's go ahead and increase that from 1 megahertz now to 50 megahertz, and we can see what happens now. We're going to keep everything else the same. Here is 50 megahertz. If I can enter it here. There you go. 50 megahertz. There's 50 megahertz. I'm going to zoom in and check it out. Once again, we have a much more sinusoidal response. We do have a slight asymmetry between the top and the bottom. You can see that the top is 311, the bottom is 436 millivolt. That's exactly what InstaView also told us, that there's an asymmetry in the signal there as well. There you go. You can see that it works, and in fact you get a fairly good idea of what's being applied to the DUT. Now, it's not supposed to replace an oscilloscope, of course. It is supposed to help you catch an issue when you don't have an oscilloscope handy at the input of the DUT, to make sure that the signal that's being applied is very close to what you expect it to be. And this can be very handy without occupying input of an oscilloscope and without having to disturb the input of the DUT. So let's go ahead and take a look at some of the arbitrary function generation capability of this instrument. Now, I spoke a lot about the basic functions, and I think a lot more needs to be included, because some of the competitors, especially the Chinese manufacturers, have so many built-in functions, and this would be very helpful because you don't have to create them from scratch. Having said that, that is of course completely possible. It's just a matter of doing a firmware update. You can also see from here that there is an add app button here, which is not active right now, and this shows there's a lot more that they intend to do. This is a platform for them to build on top of and continue to adding functions and capabilities. So let's go in the ARP builder, which then will be built into the advanced functions afterwards. So in the ARP builder, you have a couple of options. You can create your waveforms just by freehand drawing them if you wanted to, but of course I like to enter them using equations, and the math interpreter capability of this instrument is one of its strong features. Allows you to create non-linear and piecewise linear functions fairly easily. So let's go in the equation editor here, and here I've already typed one equation just to show you the extent of the complexity you can do. This, by the way, shows that you absolutely need a keyboard with this unit, and I really hope that they add that feature soon, because of course you can have a keyboard here and do it with a keyboard, but it would be so much faster and so much easier to do it using a external keyboard. And some of the placements of the buttons don't quite make sense because you have to go back and forth between the characters and this, and it needs a bit of work to make it really nice, but it works reasonably well. And the waveform editing function should be more like a cell phone. It's kind of stuck somewhere in between Microsoft Word, say, and it's an iPhone. So I think there's some work to be done, but it works reasonably well. So here you have a settings where you can basically tell the instrument what sample rate you want this waveform to be interpreted at and how many samples you want, and then that is fit into the range function here. You can see at the very top. So I'm creating a 512 nanosecond duration waveform there, and the way I have written this equation is that a single lowest frequency of that waveform is 1 cycle within the equation. So if you look carefully here, this is nothing more than 10 different tones added all together. So it's a 10-tone signal with a randomized phase roughly, so that they don't add up to give you an enormous peak to average ratio signal. So this is very simple from that point of view, and I can go ahead and compile it, and once I do that, you can see the compiler is successful, and you get a waveform over here, and this is 1 cycle of it, 512 nanosecond or 1024 points. And of course it looks messy because it's got 10 different tones in it, but spectrally the spectral content of this waveform is really well defined. It's defined by the 10 waveforms that are inputted over here. And once you're satisfied with that and you compile it, you can also save the equation and load it and do all those other things, of course. You can go OK, and you get that waveform here in the editor. And here you can do further editing on it if you really wanted to. You have a couple of options. As I said, you can draw on it. So you can go ahead and draw vertical lines, horizontal lines. You can do a freehand draw. You can do all of those things. Not necessarily what I would, like I said, what I would to do on this waveform. I'd rather do it with the equation. So let's go back. And then over here you can see one of the other things we can do is you can resample it. Now the resampling allows you to do interpolation, whether linear or sine x over x, between your samples, or to create more samples. So instead of having 1024, let's say you want to have 10 times as many samples, it can do interpolation for you. The advantage of that is that then you can change the sample rate and change the fundamental frequency of your signals without having to recompute them, which can be pretty useful. One thing that is missing that should absolutely be added is that there is nothing to scale this vertically. I couldn't find any way in here to change that. I couldn't say, okay, squeeze the signal, even though I can go ahead and edit. I can do inverting and mirroring. I can copy sections and paste them, but I could not find a way to scale them. That should be absolutely required, because you have a plus and minus 2.5 volt window here. If you go outside of that, which you can easily go outside because this is a mathematical function, then you cannot put it into the memory. So what you have to do is you have to scale it manually. In fact, if you look at my equation, you can see that I have a 0.25 multiplication at the very end. I have that simply because I could not find any other way to scale it. But that can again be really easily added. Just like you can resample it, you can also rescale it. So that should not be an issue. And once you have this, you can go ahead and save a waveform in memory. You can make 10, 100 equations. It doesn't matter how many you want, and you can save them all and store those waveforms in memory for you to use later. Once you have those, then you can start building fancy waveforms in the sequencer. But I think the math interpretation functions here can be really useful, especially with the keyboard. Now once you're satisfied with your waveforms, you can just exit this. We don't want to save this. I've already done that. And if you go under the advanced function here, here is where you can now start to create some really interesting waveforms. So you have a couple of options. You can create a sequence, a continuous, a trigger, or a gated waveforms. A sequence means you can just drop in as many waveforms as you want. Continuous is repeating the same one. Triggered, of course, is triggered and gated are connected to how the gating of the instrument is used. You can have an external trigger going in and beginning your waveform. But even without going into the trigger, there's some really fancy things you can do in the sequence editor. So let's take a look at that. Let's go back over here. I'm going to go ahead and open the waveforms I've already saved. You can see a whole bunch of them over here. So here's go 1, 2, 3, 4, 5, and all the way to 11. So I have 11 waveforms. I'm going to open them all, and it's going to put them all here next to each other. You can see that each of them are 1024 points, which is exactly what I defined them to be. And I want to create a waveform on channel 1. Well, I can select waveform 1, and I can drag and drop it on channel 1. There it is. Now I have channel 1 is waveform 1, repeated once. There is nothing else defined, and then the next after that. So let's see what happens if I add another waveform. Let's say waveform number 2. You can see it doesn't drag with my finger anymore. It's a little bit annoying. That has to be fixed as well. But here we go. So we have waveform 1. It's going to run once. It has no wait or jump events, and then it's going to the next one, and the next one is going to run this once, and then the next one, and so on. So I can make some additional changes to that. Let's say I don't want this to run only once. I'm going to define it to run 512 times. That would mean that it's going to run the 1024 samples at 2 gigasample per second 512 times in a row before moving on to the next one. So you can now begin to see how I can create really complex waveforms this way. I can do the same thing over here, of course, 512 times, and so on. And I'm going to continue building this. Now there's two additional things here which are pretty handy, and you can do some really fancy things if you configure your instrument correctly. So for instance, I can have a wait event, meaning that the instrument is going to wait and not execute waveform 1 until that event is reached. And that event can be anything from an external, skippy command, manual, or a timer. So I'm going to use the timer function here, and it's going to become clear why once all the waveforms are done. But you can imagine that basically the instrument is going to wait until your device under test is ready to receive the signal. This allows synchronization between the DUT and the waveform much easier. Now the other thing that I think is pretty useful too is that you can have a jump event, meaning that you can have part of your waveform running no problem, and then it's going to wait for one of these events before it jumps to the address you define. So now you can do in such a way that the DUT tells the instrument which waveform it is ready for, and it's not going to receive the waveform that it is not ready for, even though other things might be running. So you can do some pretty complex tree structures of triggering. If you've watched my videos where I've done the Keithley reviews of how they do their triggering on their source meters, you can see that there is kind of commonality in the way they think about building complex trigger structures. This is one of the strengths of their software. All right, here are all the waveforms. Waveform 11, and you can see waveform 11 is then at the very end. I have to make sure that the sequence completes by going back to the first waveform, so I'm going to say go back to the waveform number 1. So now we have a completely cyclical relationship between all the waveforms, and we're going to go from waveform 11 back to waveform 1. And the only other thing I have done is that on waveform 1 I have a wait event, and the wait event is set by the timer. it means that the instrument is going to wait before the timer runs out, and then waveform 1 will be displayed. This creates a blank that allows me to really easily see the waveform and find out where the beginning is, where the waveform 1 execution is. You can also do that with triggering and gating, of course. Here I'm just doing it with a timer just to show you, and the timer can be defined over here. You can see the timer is 1 millisecond. Okay, that's good. Everything looks good. Now we can go ahead and run this, and first take a look at it on the oscilloscope and see if it's doing what we expect it to do, and then we're going to connect it to a device. Okay, let's take a look at the waveform. We can go ahead and press run, and then once we press run, it's going to compute and calculate the output, and I'm going to hook it up to the MS-05, which has the spectrum view capability, which we would need to do this test, and I can go ahead and enable the output on. There it is. There's our waveform. Let's take a close look at it. And here is our waveform directly on the oscilloscope, and as you can see, the waveform has different sections associated to it. That's not surprising because it has 11 waveforms that are concatenated after each other and is being repeated. And you can also see the blanking regions between the different sections of the sequences we have created, which is a difference between the duration of 1 segment and 1 millisecond. So that all makes sense, and I'm using those differences in order to create a hold-off trigger so the waveform isn't moving around all over the screen. Now you can also see some amplitude variation, or I should say apparent amplitude variation. That's not actually from the instrument itself. This has to do with the fact that the sampling rate of the oscilloscope has been reduced to 125 megasample per second, just so you can get some rapid captures there, but you can increase that, and of course that would go away. The waveforms are perfect. We still have enough sampling rate, which we shouldn't have any issue in measurement of our signal there. So there it is. You can see it looks nice, and we can go ahead and look at the different sections and look at the spectral content. Right now we are looking at right in the blanking, that's why we don't see anything, and I can go ahead and move that. So let me do a single capture here, so the waveform isn't moving, and we can go ahead and move this and see the different waveform properties. Here you go. Here's the first section. You can see we have 10 tones, very nice and clean, huge dynamic range here on the screen, and this is the 10 dB per division over here, and I can further move this forward. And then as soon as I hit the second section, you can see that the first tone will disappear. Now whatever's left over here has to do with the nonlinearity and the imperfections of the arbitrary waveform generator itself. This is called the missing tone test, which means that all of these tones are going to create intermodulation products, landing on top of each other and filling this missing tone all the way up. Eventually, if the signal of this circuit was really nonlinear, this would fill up all the way to the top. You can see some other effects of it, second harmonics and so on, showing up later as well. We can go ahead and go to the second section here. There you go, another missing tone, another one, and so on. And I can see this waveform would be really difficult to make without a computer if you were to do it manually. But of course here we did it very quickly using the instrument with the math interpreter. So for example, let's look at this section here. You can see we have 1, 2, 3, 4, 5, 55, roughly about 55 dBc of missing tone test rejection here, which is quite good at that with respect to the individual tones. With respect to the total power, it's even better than that, of course. So we have at least about 50 to 60 dB of rejection, or in worst case, I should say 55 dB of rejection. But this is from the unit itself, and of course the scope includes that as well. Now we want to inject a DUT in between the scope and the instrument, and we can see how a DUT, let's say some kind of an amplifier, can damage this missing tone, and then it's going to become much, much worse, and we can explore that by using, of course, the device. So I'm going to pick an amplifier. We're going to try that. And here's our setup for our amplifier. I have a mechanical attenuator here directly connected to the output, and that goes into the input of my amplifier. And the amplifier is powered by the Keithley power supply here at 15 volts. This allows me to change the input attenuation to the amplifier while maintaining a constant output from the unit itself, and that changes the behavior of the amplifier. Of course, as I reduce the attenuation, it has to produce more output power, meaning it's going to get pushed into nonlinear region easily. And I can also change the power supply and see the impact of that on the output as well. So we can do the missing tone test in this configuration. So let's take a look at the output of the amplifier. So if you note over here, I have the amplifier input to maximum attenuation. So this means that the signal arriving is already quite a bit smaller than what we were looking at coming from the arbitrary waveform generator. And the amplifier, of course, amplifies that. Now if you look over here, you can see that we have already a worse missing tone test than we had before, even though we're producing less power. And I'm going to increase the power from the amplifier by reducing the attenuation, and have an eye out on what happens to this missing tone test. And by the way, before I do that, I can move around, of course, and look at different missing tone tests. And they're all going to have roughly the same kind of performance because the bandwidth of this amplifier is larger, and you can see in some cases the situation is a little bit better. Here you go. For example, this one is a little bit better. So let's go over here and look at the one we were looking at. Let's say this one. Okay, I'm going to increase the power here slowly. You can see the amplitude is going to grow. There you go. It's going to be a bigger jump and another big jump. And take a look. You can see that we are quite a bit worse than we were before. Compare this to what we were getting from the unit earlier. Now we have 1, 2, 3, about 35 dBc from one of the tones in the missing tone test. That's quite a bit of a degradation. And I can go ahead and look at some of the other ones. You can see they're all roughly about the same. And this shows how much damage this amplifier is doing to the signal and how much better the ARP was to start with. And of course, the ARP has to be much better because it has to be essentially an ideal instrument as far as the device under test is concerned. Otherwise, you're measuring the imperfections of the instrument itself, which you don't want to be doing. So let me go ahead and now reduce the power supply of the amplifier. When I reduce the power supply of the amplifier, I'm going to force it into more and more nonlinear operation. And we should be able to see the effect of that as well. So let's pick one of these. Let's pick this one. And I'm going to change the power supply. So right now we're at 15 volt DC. I'm going to reduce it 1 volt at a time. Here's 14, 13, and check out what's happening. If you look very carefully, you can see that the output power of the amplifier is not changing, but we are getting significantly more nonlinear. Eventually, we're going to reach a point where the output power is also going to start going down. There it is. You can see everything going. Now the missing tone test is completely gone. You can see the amplifier is totally saturated on one end. So let me go back up and show you a couple of other interesting features. The other thing to note is that you can see that this first tone is lower than the second tone. That's because the amplifier has a bandpass response starting at around 5 megahertz, so you have some attenuation there. But you can clearly see that a missing tone test like this can reveal imperfections of the amplifier. And this is a really tough one, by the way. And I can go ahead and look at all the other ones. You can see they will all suffer similar problems. And all the second order harmonics are now also visible, which were completely invisible before. I can go back to 15 volts. You can see that the second harmonics are quite a bit smaller. There are also computer softwares and everything you can create waveforms on the PC. I'm going to save that for a different video as this one is already quite long, but I hope it gives you a good idea of what's going on in this. Some quirky things on the GUI, but really promising instrument with a lot of potential of developing some fancy applications directly on it. And there you have it, an extensive look at the Tektronix AFG31000 series arbitrary waveform generator. I hope that you enjoyed it. You can always support the channel through Patreon and subscribing and liking and commenting, the usual stuff. But if you also want, you can support the channel by letting different manufacturers know that you enjoy these videos and that you take them into consideration when you purchase this equipment, that they are informative for you to be able to make decisions on how to equip your lab. This is very useful for me because it allows me to maintain a good relationship with these vendors and continue to bring you state-of-the-art equipment here in the lab, take it apart, and see how it works. Well, I hope you liked it. I'll see you next time.